And there are three main themes of work that we do there. Obviously, I'm going to talk to you today almost exclusively on the health monitoring side, because that's the course. But I just wanted to mention what the other ones were and how they fit together. So the research theme, the top one, is called Systems Architectures. So that is all about the types of processes you have on your engines, how you connect processes together, how do you link between different parts of the engine system and communicate between it. The systems architecture looks at sensor technologies, which are obviously key to the health monitoring, as we'll see, and also to wireless technologies, which are also very useful for health monitoring. The second part of the research is advanced control, looking at the actual control laws that happen. So I'm sure you've done modules already looking at various different control strategies, and that advanced control looks at those aspects. And then finally, my work package, which is the health management technologies, we'll come on to later. There is an overlap between all those technologies, of course, all those different themes. And together, these themes try and move from the present day situation for gas turbine engines to a future vision for an intelligent engine. Today, a gas turbine engine is extremely reliable, extremely safe. It's highly tuned piece of machinery that is optimal nearly all of the time. The problem, though, with those three things is that it's very expensive to make that system work like that. It takes a lot of development effort to be able to produce this highly tuned bit of equipment, and a lot of redundancy, hardware redundancy is needed. So through these technologies, we look at improving that and improving almost the flexibility, I suppose, of the engine. Being able to predict when things are going to go wrong means that we can do less checks on the system. You don't have to do as much scheduled maintenance on a gas turbine engine. So I suppose currently what happens is an engine flies around and mechanical engineers have worked out what the life of various components are. And after that window has expired, after it's run for that long, we would change that component, regardless of how much life is left on it. So potentially you're throwing away lots and lots of value every time you swap out that component. So part of health management technologies is trying to predict the real degradation, the real amount of wear that component has suffered, to choose the best time to replace it. So it's still got to be safe, but we don't want to take it off too early because we throw away a lot of money by doing that. So to assist with that kind of idea of optimally maintaining engines, we are looking at concepts such as being able to take the engine, connect it to the internet, query the engine, and ask it questions about itself almost. So we might be able to tell the engine, if we think there's something maybe a bit wrong, we might be able to tell it to increase the sample rate, for instance, on the sensors that it picks up. We might be able to download data from that engine to be able to analyse it, to see what happens, see what is happening in the engine. And that's all supported by having more sensors and connecting those sensors up wirelessly. So we're trying to go from today, highly tuned, highly safe, highly reliable, to I suppose, a more flexible, more intelligent product. Okay. So that's the kind of the UTC's goal and where we're trying to go to. Specifically, in terms of the health management, I want to just provide some motivation for why we're doing this. Go into a bit more detail as to what I just said, I suppose. I want to talk about how do you design an EHM system? How do you practically justify putting health monitoring onto something? You know, there's always has to be a business reason for doing anything in engineering. And one of the things we were tasked with at the UTC was to help them develop a process to be able to assess when and what do you need in terms of the health monitoring. And then I'll go more into, well, touch on the algorithm design, some examples of where the kind of algorithms you've been studying this week might fit into to a gas turbine engine. And then finally, a few examples that we may or may not get time to go on to. So, I think it's fairly obvious why you might want to put health monitoring on an engine. You don't want this disruption coming in. You don't want it to break when there are passengers on the plane, when the passengers are waiting for the plane. Any sort of delay costs the airlines thousands, millions of dollars worth of money. And that's why they're willing to invest in Sheffield University and for us to look at new ways to be able to tell when things are going to go wrong. Those are the kind of things that might happen if an engine shuts itself down in flight. What I mean by a shutdown is that always what happens when something goes wrong is that the engine fails to save. It will just go, whoa, something really bad's happened, I'm going to turn off the fuel supply, and the engine will just spin down to a stop. And because there are always at least two engines, that's safe to do. Planes are designed to fly on just one engine. But when that does happen, the aircraft has to divert to the nearest airport. And next we'll show an extreme example of a real case that happened where this diversion occurred. I need to point out this wasn't a Rolls-Royce engine. This was someone else's product. But would you believe it? Something happened in service. They were flying out to Japan or something. And would you believe the nearest airport that they could land in was one in Siberia in the winter? Now you can imagine that's pretty extreme conditions. They landed this plane. They had to sort out all the immigration of people coming into Russia. They had to sort out all the hotels for people, all the ground transportation, to get the people off the plane and bus them to the nearest airport, which I'm guessing was hundreds of miles away, to pick up the next plane. They then had this plane stranded in the middle of Siberia, in, as it says there, minus 34 degrees Celsius, and having to try and repair this product and get it so they could change the engine out, put a new engine in, and all the logistical problems that came with that. I don't know if it says. So, you know, the figures are in their tens of millions to sort out this problem. So there's a huge motivation for knowing when something's going to go wrong. It's not for safety, it's for money. Rolls-Royce have the way they describe health monitoring is in 5 steps. So this is just one company's view of health monitoring. We start off with the ability to sense behaviour of the engine. Now most of those sensors are there already for control purposes, to be able to safely control the aircraft. But some of them are also there just for health monitoring. The types of sensors that are typically on a gas turbine engine would be your pressures, temperatures, and speeds at various points throughout the engine. Specifically for health monitoring, there are vibration sensors on there that are trying to detect defects in the blades. There are sensors on there called metal chip detectors. There are sensors that look at the oil. So these metal chip detectors look at they look for particles in the cooling oil system. The reason for that is you've got, let's suppose you have a problem with a bearing. It starts to wear out. What might happen? You might start getting flakes of metal being chipped off these ball bearings, and they go into the oil, into the lubrication oil. And by having a sensor to measure those particulates, we can tell that something is starting to go wrong. So those are the sensors. Great, you've got some sensors. You need to be able to get hold of that analog information in some way. So we have the next stage, which is the acquisition of those sensors. The sort of decisions that need to be made in the acquire stage are what resolution do we need to sense at? Is 8-bit resolution, quite a crude measurement, sufficient? To the extent of, is it a simple on-off? Is it there or not there, a binary signal that we're after? Or do we need to go all the way up to kind of very high cost, high sophistication sampling, 24 bits, and at very high frequency? So you look at something like temperature and vibration. anyone think what's going to be the higher sample rate that's needed for either temperature or vibration?
Vibration.
Yeah, obviously. So with vibration, yeah, you need to be able to sample this data at tens of kilohertz, and temperature, you need sort of the dynamics of the system's what kind of seconds anyway, if not minutes, to pick out the changes in temperature. So once you've acquired that data, you've sampled that data down. You then need to do something with it, and this is the really contentious might not be the right word, but there's debate as to what is the best thing to do with that data once you've got it. Should you try and process it all on the aircraft, or should you try and transmit it down to the ground station and process it on the wing? And process it on a normal desktop computer once you've got hold of it. And that decision would be made on, I suppose, how much time you've got to react to a particular fault, how much data there is to transfer. It is still, even today, very difficult to get data off something that's flying around in the sky. And typically at the moment they can only get data off 3 times during a flight, and they have to really pack that data down to make it as small as possible to be able to transmit it economically. So you acquire it, you transfer it, somewhere you analyse it. So that's the part where you start to apply your algorithms to the system. And they can be either on wing, let's say, or on the ground. And then finally, the most important thing, really, with the whole health monitoring is this final stage. And it's probably the bit that people might forget about. Once you've done your analysis and you've said, okay, there's something happening, you've got to do something about that. You've either got to replace the component, you've got to do an inspection, and that's often the art of the diagnosis, knowing what these particular, what the outputs of the algorithm tell you about what you ought to do to the aircraft. And these are decisions, that potentially could have some safety implications. They certainly have got some monetary implications. So it's very important to get that stage right. So I find that a really nice way of thinking about health monitoring generally, in the sense, acquire, transfer to some location, they analyse the data and then act upon it. Yeah. Okay. Any questions on how Rolls-Royce do it? I think we're now going to go on to some of the ways the UTC have been helping Rolls do this process and be better at analysing their engines. So if they're big challenges for monitoring, certainly within Rolls-Royce, I think everywhere really, is there are a lot of disadvantages to doing health monitoring. You might be adding more sensors, it's going to add more weight, more cost. It's going to reduce the reliability by putting more sensors on, because those sensors are more likely to fail. And there are, of course, the development risks as well. You've got to get this system working, and it's got to not give you false alarms, as we talked about this week. I'm sure you don't want a lot of disruption to be caused by the monitoring system. So this is where we've been asked to help Rolls-Royce, and we'll come on to how we have gone about helping to design these systems. So that's the first challenge. Second challenge for us, really, is the fact that these engines are too good. They're so reliable, very rarely fail. How do you actually develop algorithms? And I'm going to talk a bit about how we get hold of data, how we simulate it, what do we do to give us a bedrock to test out these different sorts of algorithms. Final point, and this is fairly specific to the gas turbine engines, I suppose, and that is, how do you get these systems to work in the very harsh environments that are on an aircraft when it's flying around all over the place? You've got, at the core of the engine, you've got temperatures 1700 degrees Celsius. So how do you monitor that temperature? Incredibly difficult to do that. You've got